All right, we're going to start section 3.4. It's exponentials and logarithmic equations. I will tell you that in regards to this is definitely a difficult section. I'm highly encouraging, again, you to take notes, which you should already be doing. But if not, this would be a good idea. Definitely take them back and certainly keep referring back to them. Keep watching them. There are other videos out there too that you can find if you just, say solving exponential equations or you Google solving logarithmic equations. That'll look very similar. The way they solve those is pretty close to what I do. There are multiple versions of how you can solve. So if those help you, you can certainly try those different versions. Let me know what you're trying, but I would highly encourage you. This is not going to be easy by any means. This is some of the hard stuff that we've done all year. So it's going to take a little bit more effort. So just want to give you a heads up. Okay, so a couple exponentials of logarithms just saying, hey, is this a solution? So is 4 a solution to that first equation? So what I would suggest you do is plug it in. So if it's saying, is it a solution? I would simply just take what you have, take this 4, and then plug it in where you see for x. So that would give me 2, and then an exponent of 4 minus 1, and basically say, hey, is that equal to 8? And you can use Desmos for some of these. So if you wanted to type in 2 exponent 4 minus 1, you could. Remember, 4 minus 1 is, of course, 3. And so you can say, in this case, well, let me actually go ahead and say, well, that's 2 to the third. Well, is 2 to the third 8? Well, yes, it is, which means, yes, it's a solution. So if you're not sure what 2 to the third is, which is 2 times 2 times 2, which is 8, certainly you can type it into Desmos, and we'll definitely do that here for the next one. So it says, is 4 a solution to this log base 3 of 2x minus 1? Is that actually equal to 5? So same thing. I can do a log base 3, and then when I plug this in, I'll get 2 times 4 minus 1 and say, hey, is that equal to 5? And I'm going to simplify this and say, well, that would be log, and 2 minus 4 would give you, or 2 times 4 would give you 8. And is that equal to 5? So then that would give me log base 3 of 7. Is that equal to 8? And you could do a couple calculations. You can use Desmos, be able to kind of do some of these too. And I'll remind you something here in a second. But if I do go ahead and use Desmos and say that, it does have, if I go to functions, go to miscellaneous, you see this log base A. So I can type log. I had a log in this case. So going back to here, I had a log base 3 of 7. That's how you pronounce that. So I'm going to type in a 3. Whoops. So go down where it has that little thing down there. That's a 3, and then type in 7, and I get 1.77 repeating. That's definitely not there. So no, this is not a solution. Another thing that you could do is you could also use the change of base formula, which we've talked about. So change of base is basically saying when you've got this log base 3 of 7, that's the same thing as the log of 7 over the log of 3. So we call that change of base. And that's one way, because if you use a TI-83 calculator and you don't have Desmos, it doesn't do a base other than this common logarithm. And a common logarithm, as you've learned before in the other videos, is a base of 10. So if you don't have Desmos and you have a regular calculator, that's what you would do. Okay, so now we're going to actually start solving some of these. And you will usually get one answer, but you could definitely get a couple of answers. Sometimes you can have what's called extraneous solutions. We'll have those discussions throughout the next week or two. So it says this one. Now, we've talked about one before where if you have, we call this an exponential because you have an exponent, that's a variable. But one thing we're kind of looking for here is, can I get both of these to be the same base? Because if I can, that makes things a lot easier. So I'm going to try to get both sides to be the same base. So I take this side with the bigger base and I try to break it down so it's a 2. Well, I actually can get this to be 2 to some power. Now, 2 to the second is 4. 2 to the third, we said, is 8. 2 to the fourth is 16. But 2 to the fifth is the same thing as 32. Now, we've also learned when you have the same base equal to the same base, you're able to just take your exponents and set them equal to each other. So I can say this exponent equal, and then the exponent on the other side. And then you go ahead and solve if you have to. Now, in this case, I don't have to solve this. This is simply just x to the fifth. So you always want to try it. Sometimes that may entail breaking both sides down, but usually what we do is we take a bigger number, try to break it down to the other base. Now, it's not always going to work. If this was 2x equal, or 2 to the x equal to 30, you wouldn't be able to do it. So we have a different way of solving that one. Okay, on this one, we're going to have to rewrite this one a little bit, a couple of different ways. First off, 1/3 is the same thing as 3 to the negative first power. That's the same thing. So I'm going to eventually get these to be both bases of 3s because I have a 3 over here, and I can change 9 to be a base. So 3 to what power would give you 9? Well, that would be the second. Now I'm still not quite there, but I do have this. I call this is like the power to a power roll. I've got a base of 3 raised to a -1 raised to an x. So what I need to do is I need to take these, and I'm going to go ahead and multiply those. That's what the exponent rule says. Well, -1 times x is -1x or negative x. And then this equals 3 to the second power. Now that I have that situation where I have both bases, I have base of 3 equals a base of 3, I can set my exponents equal to each other. So the left exponent is -1x equals the right exponent's 2. Now, this is not solved for. I need to go ahead and divide both sides by a -1. And then I'll get x equals and then a -2 as my solution. So this has an answer of a -2. All right, this one, a little bit different. You have a base of E. I'm not going to get 7 to be a base of E here, but this is one situation, and we'll do a lot of this with an E. You always want to get the E by itself. So if this E to some power is not by itself, you're going to have to do that, and we'll talk about what that looks like. But once you do, you're going to take the inverse or the opposite kind of thing. Just like if I was having a 3x, the opposite of multiplying by 3 would divide. Well, same thing. The opposite of an E is natural log. So I'm going to natural log both sides. Natural log the left side, and I'm going to natural log the right side. Now, one thing to mention is, if I was natural logging e to the x power, a reminder that a natural log is the specific log where it's log base e. And we've talked about the rule that when you have the base of a logarithm and the base of the exponent, whenever you have that situation, those cancel out and just leaves you with x. So that's why when I do this, these cancel out and leaves me just an x. So I get x here, and on this side, that's just the log of 7, natural log of 7. So that's your answer. That's the exact form. Now, if you wanted to go to Desmos and type in and go over here and do that, you can go to functions, and you have ln, and you can type in 7, and you get 1.95. So 1.95 is the same type of answer. That's just a rounded off answer. So we'll do more of these where you need to first get the e by itself, but then the next step is to take the natural log of both sides. And once you do that, these will cancel out. Just like if I have a 3x and you divide it by 3, that leaves you with the x. Okay, now let's talk about some logarithmic equations. Very similar to what we have. A lot of time what we want to do is most of the time, you want to make sure you have just one logarithm. So that means if you have a couple, we'll use our rules that we've already learned about condensing and expanding, but we usually condense them, and you get it down to one logarithm. Now, if I have a log equal to a number, I always say put in exponential form. But before we do that, I'm going to rewrite this because the natural log is that specific logarithm where it's a base of e. And then the next thing I'm going to do is I'm going to put this in exponential form. So in that case, I'm going to have e. So we go e to the -3rd power equals x. And so a lot of time what people will look at is they'll take this e to this -3rd power and then equals x. And so that's log form. Then I have to say, okay, let's solve for x and get x by itself. Well, it already is. So this is what we call exact form, or you could have 1 over e to the 3rd power. If you want to type this in the calculator, e to the -3rd, you can certainly do that. So I can do e and then exponent and then -3, and you get 0.05. Now in regards to, so these are the exact same thing. One's just, we call this an exact answer. This is more of like a rounded off answer, numeric answer. One thing is the whole domain with logarithms always has to be positive. So if I take a natural log of something, it's got to be bigger than 0. So if my answer was a negative, that would be extraneous. I wouldn't be able to do it. It wouldn't be a part of its domain. In this case, I don't have that. All right, this one. Okay, log and then of x. Reminder that when you have that, this is a common logarithm. That's a base of 10. So we're going to put this in exponential form. So I'm going to take, this is my base, goes to there. So the first thing I'll have is 10 to the -1st power equals 8. So we practiced this before, but certainly worth mentioning. We're putting this exponential form. I would write that down so when you refer back to it, you know, hey, what did you just do? That's really the same thing as 1/10. or you get 0.10 as your decimal. But again, that's a positive number, so I'm okay. Reminder that with graphing of exponentials, any answer positive or negative is okay. The domain of an exponential function is all real numbers. Anything is okay. In this regard, though, with logarithms, it's not the case. My answers have to be positive when I go take the natural logarithm up. And then the last one, log base 3 of x equals 4. Same thing. Let's put in exponential form. So this 3 to the 4th power equals that. So base of 3, exponent of 4, then equals, and then x there. And so this is 3 to the 4th power, which is 81. So these are the kind of starting off points that we're going to kind of work on. We'll slowly build, but it's super important to learn these basic ones because the harder ones are going to do a couple of steps, get down to these basic ones, these easier ones, and then we'll finish them off. So super important. I would highly suggest maybe watching this video a couple of different times.